Hi, I'm O. Today I would like to share with you a practical example on cantilever retaining wall design, part 2. This video shows how to perform an ultimate limit state design for a cantilever retaining wall, whereas part 1 of this video shows the stability checks on the retaining wall, and it is prerequisite to this video. These are the design inputs for a retaining wall. Soil parameters such as height of retained earth, density, internal friction angle, friction coefficient, bearing capacity, and retaining wall parameters such as characteristic strength of concrete and steel, unit weight of reinforced concrete, estimated bar size, nominal cover, mean tensile strength, and the action surcharge. Provided also the geometry of the retaining wall, dimension A, B, C, D, E, F, G, and the width and the height of the wall. The pressures acting on the wall or stem, toe, and heel need to be determined. The pressures acting on the wall are exerted by the soil and surcharge. The active soil pressure can be calculated using equation 1, which requires gamma, the density of the soil, h, the depth of the soil measured from the topmost of backfill, w is the surcharge, and the Rankine active pressure coefficient Ka can be obtained using equation 2 that requires information on internal friction angle, phi. Remember, we need to obtain bending moment and shear force at the face of PQ. Pressure is calculated only from h equal to 0 to 4 meter. In this case, when h equal to 0, the pressure is 3.33 kN per meter square, and h equal to 4 meter is 28.67 kN per meter square. For toe and heel, the pressure was based on bearing pressure calculation. The bearing pressure can be determined using equation 3, where the N is also the vertical force Vk and moment M is Vk multiplied with the eccentricity Ec, and Y is half of the base width B divided by 2. Bearing area and the moment of inertia can be determined based on the bearing width, which is also B, and the length is 1 meter. Detailed calculations of Vk and Ec have been explained in part 1 of this video. In addition to the bearing pressure, we need to account for the pressure exerted from the vertical components, such as the weight of the concrete and soil, as well as the surcharge. In this case, the concrete base with 0.4 meter depth impose a pressure of 10 kN per meter square, whereas the soil and the surcharge impose pressure of 86 kN per meter square. It is noted that the maximum and minimum bearing pressures act upward on the base, and the pressures from the concrete, soil, and surcharge act downward. Let's have a closer look on the interaction beneath the base. A net pressure can be obtained by summing up the upward bearing pressure and the downward vertical pressure. It can be seen that the net pressure of 96.52 kN per meter square acting on toe goes upward, while 44.98 kN per meter square is acting downward on heel. We can skip determining the base region below the wall, as we only need to determine bending moment at face PR for toe and face QS for heel. Once we have determined the pressure, we can obtain the shear force and bending moment for wall, toe, and heel, treating this component like a cantilever beam. For example, the wall is fixed at PQ and the load is acting laterally. If we rotate the system horizontally, it looks exactly like a cantilever beam or slab. Since the lateral pressure is a trapezoidal loading, we can subdivide the loading into rectangular and triangular loadings. Then we can get the shear force from determining the area of the rectangle and triangle. Remember, factor of safety 1.35 is to be applied to GK, which is contributed by soil or triangular loading, and 1.5 for QK, which is contributed by the surcharge. Bending moment can be obtained by multiplying the loading with the lever arm, measured from the centroid of the area of interest to face PQ. For example, for rectangle loading, the lever arm is half height of the wall, while for triangle, it is 1/3 of the height. The same technique can be applied for analysis for toe and heel. The maximum bending moment and shear are taken at face PR, whereas for heel it is at face QS. As we can see here, the net pressure acts upward at toe and acts downward at heel. Similarly to the wall, the analysis becomes easier to divide the total pressures into triangle and rectangle pieces. Shear force diagram and bending moment diagram can be plotted after the analysis. The design of main reinforcement can be done using the slab procedure outlined in Eurocode 2. The procedure includes the determination of K, Z, and AS using the shown equations. The equations for K requires inputs such as M, which is the moment taken from analysis result. Since the wall is designed per meter run, the width B is taken as 1 meter. The effective depth is calculated based on the thickness of the face PQ, PR, and QS. And characteristic strength of concrete FCK is 30 megapascal. Equation Z requires information of K, AS requires information of Z, and FYK is characteristic strength of steel, 50 megapascal. It is to note that it is more practical to make sure the K is lesser than the K balance, or equal to 0.167, to avoid the usage of compressive bars. And if the Z is greater than 0.95D, only 0.95D is used. Referring to the direction of the pressure, AS provided shall be placed vertically at the wall near the face, contact with backfill. Similar process can be applied to toe and heel in obtaining the main reinforcement. In this case, for toe, AS provided shall be placed horizontally at the bottom part of the base. Whereas, for heel, AS provided shall be placed horizontally at the top part of the base. Main reinforcement shall be provided within the minimum and maximum values recommended in section 9.2.1.1. AS provided are suggested for the wall, toe, and heel as H12 100, H12 200, H12 125 respectively. The secondary reinforcement is proposed for transverse reinforcement and surfaces that requires only minimum reinforcement. For shear design, the larger value of shear resistance of the concrete, VRDC, or the minimum shear shall be greater than the shear forces at the wall, toe, and heel. VRDC and V minimum are expressed using the shown equations and require information such as AS1, which is the AS provided. In this case, the minimum AS provided is taken for the check. FCK, B, and D are the characteristic strength of concrete, width taken as 1 meter and the effective depth respectively. It can be seen that VRDC and V minimum in this calculation are both greater than the shear force at the wall, toe, and heel. Therefore, the check is satisfactory. Cracking control is recommended by EN2, Eurocode 2, section 7.3.3. The steel stress is determined for case under quasi-permanent loading, and the detailed calculation for GK and QK is shown in part 1 of this video. Let's have a quick revision on the analysis of forces in the retaining wall system. Vertical and lateral forces are determined for stability check of the wall. The vertical forces consist of surcharge and weight of the systems, such as concrete and soil, whereas the lateral forces are contributed by the active pressure from surcharge and soil. Here, the total vertical force GK and QK can be determined by summing up the appropriate forces from item 1 to 5. The allowable bar spacing is then determined from table 7.3n based on the steel stress. Considering the design crack width of 0.3 mm, the recommended maximum allowable bar spacing is 200 mm. In this case, all the proposed bar spacing is lesser than the maximum allowable. Therefore, the check is satisfactory. This is the detailing of the retaining wall. We can first detail the reinforcement based on the detailed design solution. For instance, for wall, the reinforcement H12-100 center to center is placed vertically at the wall at the side next to the backfill. Knowing from the bending moment diagram, the moment is reducing towards the end of the wall, where the wall at the thickness of 200 mm. H12-100 center to center can be reduced to half, and the curtailment can be placed at the half height of the wall. Then, for toe, H12-200 is placed horizontally at the bottom of the base, whereas for heel, H12-125 center to center is placed horizontally at the top of the base. Next, the other side of the wall, which is not subjected to any tension, AS minimum or H12-200 center to center can be applied here. AS minimum shall also be applied for the transverse reinforcements for wall and the base. To ensure the system from water pressure, the drain pipe and whip hoops can also be provided. Now, it is your turn to solve a given problem. You are to propose a retaining wall design which is capable retaining earth of 5 meter height and with the given soil properties. Remember, stability check for the wall is necessary. I wish you have a good time in exploring both Part 1, the stability check, and Part 2, the ultimate limit state design for a retaining wall. See you in my next video.